Thank you very much. It is an honor, first of all, to be invited to speak at the conference for Harishchandra. Of course, people in my generation never met Harishchandra, but we grew up mathematically hearing his name. And I also remember how Langland was always talking very highly of Harishchandra and insisting that we are continuing along the lines, along the path taken by Harishchandra. It's also a pleasure to be back in India. Like Jeff Adams, I was also scheduled to come here in that dreadful spring of 2020 for Dependra's conference, and that trip was cancelled only a few weeks before, so it's great to be back. What I would like to talk about today is I would like to convince you that L functions, which are usually understood as some object of interest to number theory, may have some very, very significant role to play in questions of harmonic analysis. And when I say harmonic analysis here, I mean mostly harmonic analysis of the type of symmetric spaces and more general G spaces over a local field. So I will also talk about global harmonic analysis and automorphic forms, but the main type of questions that I have in mind for this talk have to do with the question of distinction, for example, that we heard about. So suppose that you have a group G acting on some space X, and you want to consider which representations pi appear in the space of functions on X, everything over a local field. Or equivalently, by dualizing, this could be thought of as which representations pi or pi dual are irreducible representations, are quotients of the space of Schwarz functions on X. If you don't know what Schwarz functions are, you can think of it as CC infinity. So over a non-Archimedean place, it will be CC infinity. Okay, so by the way, I also spent the first 2 days sitting in the in the second half of the lecture room, and I know that it's hard to read. So if my font takes a negative derivative at some point, please warn me and shout. Please do me the favor. Okay, so what do all functions? I also want to make some disclaimers before I get to the talk. So disclaimers. So certain details will not be presented with precision. For example, I will not talk about how to choose Haar measures. I will not talk how to choose an additive character of my local field. It's going to have to be unitary. Let's call this character psi. There will always be choices like that will not be clarified, but they can be clarified. It's just going to get too technical. All right, so the first place where L functions show up in local harmonic analysis is in the Plancherel formula of Harishchandra. So consider a reductive connected group G over F, and again, F is a local field. It can be Archimedean or non-Archimedean, and when it's clear, I will write just G for G of F. Or actually, sorry, let me call this H for reasons that will become clear. So you have a map from test functions on H to the space of Hilbert-Schmidt operators for any unitary representation pi. So let's call this map. So f goes to pi of f. And the Plancherel formula says that you can compute the L2 norm of f you can decompose the L2 norm of f into these Hilbert-Smith operators, into these Hilbert-Smith norms. So this will be a direct sum over classes of parabolics, conjugacy classes of parabolics in H of the integral. Well, sorry, I'm decomposing the norm here, so I'll write the sum of the integral of pi of f. Well, so the integral will be over the discrete mod center representations of the levy of pi, of p. And then we take the induced, unitarily induced representation. We take the corresponding operator, Hilbert-Smith norm, and then the formal degree, the Plancherel measure of sigma, times d sigma, where d sigma, times some, actually let me write here nu of sigma, and I will clarify. So this is the Plancherel measure. And of course here I have to divide by some symmetries, so the parabolics should be taken modulo an equivalence which is called being associate. So this equivalence here, P is equivalent to Q if, up to conjugacy, if they have conjugate levies. And here I'm also overcounting by the order of the Weyl group elements that take a levy, the levy to itself. So more abstractly, another way to write this theorem is to say that the L2 space of H is the space of invariants. So it's a direct sum. I'm gonna take care of these symmetries at the end by putting some invariants here that I will explain. But it is the direct sum over all conjugacy classes P of parabolics of the direct integral. Here I'm not going to divide, I'm going to take sigma in discrete representations of the levy. And here I'm going to take the space, the Hilbert space of Hilbert-Smith operators. Nu sigma. So the L2 space of it is a subspace of that, but it can be identified with a space of invariants. What do I mean invariants? So invariant means that for means that operators invariant under the intertwiners meaning whenever you have Q associated to P and here and then there is a standard intertwining operator, there's a standard family, meromorphic family of intertwining operators. Here I'm not going to use the standard notation, I will write R for the intertwining operator. So let's say that Q and P share a Levy subgroup. So then I have an intertwining operator from the induced representation sigma from P to the induced representation from Q. And of course, the action of the group, this intertwines the action of the group and the Hecke algebra and the Schwarz algebra, so that means that it has to be. Oh, by the way, maybe I said I will not define Schwarz space, but this is not yet the Harish-Chandra Schwarz space, so I should have clarified it. So I said it here, these are rapidly decaying functions. So actually for today's talk, you can take this to BCC infinity of X, okay? So I'll get to the Harish-Chandra Schwarz space in a moment. Okay, so invariant means invariant under those operators, commuting with these operators. Is that clear? So there's no L functions yet, but the L functions show up when you consider the Plancher L measure. So what is nu of sigma? Of course, first of all, sigma lives in a family. So sigma lives in a family. Any such sigma can be twisted. So sigma can be twisted by characters of the Levy. And therefore, in this family, we have a Haar measure d sigma, which, like I said, I'm not going to specify Haar measures, but it's going to be some choice of Haar measure that matches my other choices of Haar measures on the group. Then we have the formal degree of sigma, which is simply its Plancher L measure on L modulo the center. And then we have this function mu of sigma, and mu of sigma is the scalar mu of sigma is the scalar composition of the intertwiner from P to its opposite, composed with the intertwiner from the opposite to P. Sorry, is the inverse. The inverse of mu sigma is the scalar composition of these two intertwiners. Or equivalently, the inverse of mu of sigma is the scalar by which the intertwiner acts on the square of the L2 norm, or on the square of the norm of this unitary representation. Okay. And you still haven't seen L functions, but here is a conjecture of, if you combine the conjecture of Langlands, which is a theorem in many cases by Shahidi and others, in many cases. Together with the Hiraga-Ichino-Ikeda conjecture, which again is a theorem case of classical groups by Bézard-Plessis and others. So these two together imply, that nu of sigma, so the combination nu of sigma is equal to this Haar measure times the gamma factor of the adjoint representation. So maybe up to a small rational number. Let me not get into it here. This is the gamma factor of sigma on the adjoint representation on H modulo the center of the dual levy. So let me just add something to my disclaimer just to simplify the formulas. So the formulas will be for split groups. So otherwise I have to take some Galois invariance here. So, and the gamma factor is the gamma factor that shows up in the local functional equation. So, let me remind you that given well, again, I'm going to present formulas for split groups. So, let me assume that I have a split group and a representation of its dual group. The gamma factor is related to epsilon factors and L factors like this. None of these quantities is easy well, neither the gamma factor or the epsilon factor is easy to describe explicitly in every case. In fact, without the local Langlands correspondence, these things don't make sense, or the L function doesn't make sense. But let me remind you that sigma here. That if you have the Langlands, if you give yourself the local Langlands correspondence, which actually now we have, at least it's semi-simplification, which is enough for these gamma factors, we have, to sigma is associated a Langlands parameter from the appropriate version of the Galois group, some Weil or Weil-Deligne group, to the dual group, and these L factors can be defined as arcing L factors. So, for example, at every non-Archimedean place, you would have that L S sigma R is equal to 1 over determinant of I minus geometric Frobenius minus phi R composed with phi of Frobenius restricted to the inertia invariance of my representation. Anyway, so these are formulas that already seem completely indifferent to harmonic analysts.
Excuse me.
Yes.
But gamma may depend on psi.
Yes.
But the absolute value does not.
It doesn't if you choose the measures and the psi compatibly. And I said that I will not talk about how. So there is a formula of the following form that, suppose that you have a character, for example, if you consider everything reduces to one-dimensional, and if you have something like that, you change psi by some non-zero a, then there's a formula that I don't remember it very well. It's something like chi of a to the s gamma without the a. Some formula like that. So the absolute value will depend. The absolute value may depend, but then you have to choose your measures to be self-dual with psi and things like that. So I'm not going to. Okay. Okay, so these are already formulas that would make a harmonic analyst look away, I think. So, where am I getting at? Let's forget these formulas for a little bit and go back to this description of the Plancherel measure in terms of some black box, which is the formal degree of the discrete series, and this scalar, which is the scalar composition of the intertwining operator with itself. So I would like to change the formulation up here and remove the scalar. Okay, just work with a Haar measure times a constant. Okay, there's a very nice way to remove the scalar, which is the following. Instead of mapping the Schwarz space to sorry, that was a different story. So instead of mapping the Schwarz space of H to Hilbert-Schmidt operators of my representation, and what are Hilbert-Schmidt operators of my representation? Hilbert-Schmidt operators are the completed product of pi and pi bar, a completed tensor product. And in this case that we're discussing, the induced case, we have the induction from P sigma, induction from P sigma bar. So instead of considering this map, I want to compose this map with the inverse intertwining operator in one variable. So for example, let's take the second variable. And once you compose with this map, you're going to the induction from P of sigma tensor the induction from P opposite of sigma dual. Okay? And then you might even want to take the so this operation here is not unitary, okay? So you can express this operation will absorb this factor, okay? So you might as well, instead of taking the Hilbert-Schmidt operators, take this Hilbert space and consider this morphism from here down to here. And that's going to give you a Plancherel formula with different norms here and without the mu factor. Okay? Now this turns out to have a meaning, to have a geometric meaning. If I compose with the matrix coefficient, of sigma, then I end up in the induction from P times P opposite to H times H of functions on the levy, because that's where the matrix coefficient of sigma lives. This induced representation can also be written. So here I'm switching secretly from the unitary spaces to their smooth vectors, and I'm not going to be very careful about this. So really I should put smooth vectors here, but it doesn't matter. So this space here is functions on the following homogeneous space for h times h. You take h times h and you mod out by the unipotent radical of P. Well, let me write it first this way. This is the levy, but the levy has a two-sided action of the levy. So both parabolics act on the levy through the quotient, and I take contracted product. In other words, I take the product and I divide by the action of P times P minus of this. This is a homogeneous space for H cross H, which I will call H sub P, and I'll give it a name. It is a boundary degeneration of H. Notice that it has the same dimension as H. Okay, and another way to think about it is this is H cross H over the unipotent radical of P times the unipotent radical of P bar times L diagonal. Of course, if P is H, I haven't done anything, H sub P is H. So these degenerations are some kind of cones, or they belong to some kind of cones that model my space H at infinity. So let me give just the simplest example. So, for example, if H is SL2, so these are matrices of determinant 1, then H sub Borel is rank 1 matrices. And if you want, you can think of this space as kind of degeneration of your, so you have this family here, the family of 2 by 2 matrices, mapping down to the affine line through the determinant. And the general fiber, and this is a space for under the action of H cross H, of course. And the general fiber is, at least over the algebraic closure, isomorphic to SL2. But then the special fiber consists of the zero matrix and the matrices of rank 1. Another example to keep in mind, or actually I'll give more, so this example is enough for the group case. So here is now a reformulation of the Plancherel formula L2 of H, I erased it, but I'll write down the same thing, is the sum over conjugacy classes of parabolics of the direct integral, so here's a very nice way to write it, is the direct sum over conjugacy class of parabolics of L2 HP discrete, and then some kind of invariance property. What is L2 of HP discrete? Is simply the unitary induction from P times P bar to H times H of L2 of L, right? Because our space is induced. Okay? So this is a very nice formulation of this theorem, except that I have to tell you what are the invariants here. Okay. Sorry, and I think I realize now that I'm forgetting some constants that have to do with yeah, so I should be dividing everywhere by, also in the previous formula that I wrote, by 1 over the order of this Weyl group of LP. Sorry. If you want to be compatible with the norms, right? But now, what are the invariants? So here, inv means invariance under the so-called scattering operators. And those are very simple to describe because the maps, if you compare with the space of Hilbert-Schmidt operators, we then applied an inverse intertwining operator. So we knew what invariance meant here. So it's very easy to describe what invariance means here. So after spectral, so these are the scattering operators are operators indexed by, you know, associate parabolics. Yes. Discrete, yes. Here, yeah, this should be discrete, yes, of course. I'm inducing the relatively discrete mode center spectrum, yes.
You mean discrete mode center?
Mode center.
There has to be the A component.
Yes, it is discrete mode center, but this is a very clean way to say it. Really, I'm not modding out by anything, it's discrete mode center.
But actually I have another problem. Is that right here you have a natural empty space. You have a homogeneous space, so there is a natural empty structure. On the other hand, in the Chandler's formula you have a new function. So you are asserting that this is compatible.
Yes, because remember the Plancherel measure was the mu function times the formal degree times d sigma. This here is Plancherel for L discrete, L2 of L discrete. This here was absorbed in my operators because I composed with an inverse intertwiner.
So you're not writing the same Plancherel formula.
It's not the same because my map has target not here but here. And the maps differ by this inverse. Okay. And now what is the scattering operator? The scattering operator is an isometry between L2 of HP and L2 of HQ. An isometry, of course, which is H cross H equivariant. The fact that this is an isometry corresponds to the so-called Mass-Selberg relations. And if you decompose here spectrally, so of course, okay, so here I should put discrete again. In fact, you can make sense of this isometry for the entire spectrum, but if you decompose, so after spectral decomposition, this operator decomposes into what I will call SQP comma sigma. So what will be SQP comma sigma? It has to go from induction from P times P bar of sigma tensor sigma bar to induction from Q times Q bar of sigma tensor sigma bar. And it will be given by a formula that you can work out from these definitions here. So SQP is going to be the standard operator for P times the inverse of the standard operator for Q. Now you might complain that there is an asymmetry here. Why inverse in the second copy and not in the first copy? Well, as a matter of fact, this turns out to be the same if you put the inverse here. You could put the inverse in the first copy and not in the second copy. It will not matter. And now, let me introduce L functions again. We have said that the difference between the inverse Radon transform and the Radon transform is this mu function. So I can rewrite this as the mu function of sigma. Maybe I need an inverse. If I need an inverse, I'll figure it out later. Sorry. And this, as we explained before, this has to do with gamma factors. Okay, so yeah, so this is, I think this is the mu function inverse. So this will be equal to gamma of 0 sigma h check mod L check psi absolute value inverse. Okay, so still we haven't seen any serious harmonic analytic implications of that. Let me just mention that the Plancherel theorem also has, so we also have a version for the Harish-Chandra-Schwarz space. I hope everybody knows the definition, but if you don't, I will not say this here. So it says that a way to formulate the corresponding theorem of for the Harish-Chandra-Schwarz space is to say that the Harish-Chandra-Schwarz space of H is equal to the same. Actually, let me just modify what I wrote there. So you can say that the Harish-Chandra-Schwarz space of H is equal to the same thing, invariance under the same operators. And this is precisely a reformulation of Harish-Chandra's theorem, which represents those as C-infinity sections of the endomorphism bundle. Exactly the same statement after you compose with these intertwining operators. And now we'll play the same game with other homogeneous spaces. So same statements, so the analogous statements hold for symmetric and more generally spherical G spaces X. So that's why I didn't call my group G, because in the group case G is H cross H and X is H. So that's what we're generalizing. So namely, each of these spaces X, to each of these space X, you can attach a root system And let me denote by delta x the simple roots and by Wx the Weyl group, the so-called little Weyl group of the variety. So classes of parabolics in the group case are parameterized by subsets of the simple roots, and the same story holds here. So for any, instead of saying for any class of parabolics, I will say for any subset I of the simple roots, there is a boundary degeneration xi of x. This xi has an action of, has the same dimension and it has an action of the group. So the example to keep in mind here is just take x to be SO2, SO3 mod SO2. So what is SO3 mod SO2? SO3 mod SO2 is the level set of a quadratic form. And then x corresponding to the empty set, that would be the Borel in my group case, is going to be the asymptotic cone of this hyperboloid. So it's going to be q equals 0 without the 0 point. Sorry, everybody knows that when you draw a hyperbola, you should start with the asymptotic cone and then draw the hyperbola. So this is x, and this is its asymptotic cone without the origin. And there are similar theorems. Now this here, so the Plancherel formula, and here I need to put many names. Let me say them instead of writing them for, you know, for symmetric spaces over the reals, Van den Barsch, Lichtrul, and Delorme. For spherical spaces split over the p-adics, my work with Venkatesh, symmetric space, general symmetric space over the p-adics, Delorme, general spherical spaces and more generally general spherical spaces over the reals, recently Delorme on a work based on a lot of joint work with Krotz and others, also for the most continuous spectrum work of Eitan, Sayak and Job Puit. Many names, so you see why I'm not writing them. But in any case, the Plancherel formula can be formulated as follows, that there is a canonical isomorphism of unitary representations from L2 of x to the direct sum over subsets of the simple spherical roots of L2 of xi discrete. Again, discrete means mod center, and center here means that, you know, you have more symmetries on the cone. You have some multiplicative group acting, so it's going to be discrete modulo the action of these extra multiplicative groups. And then you take invariance under the Weyl group. Invariance under something. So, and what is that something? So, sorry, let me leave this here. No, it's invariance under the analog of the scattering operator. So this here were the scattering maps in the group case, and similarly, in the general case, you have so here inv means invariance under the scattering operators. These are again isometries as ji from L2 of xj discrete to L2 of xi discrete when j is associated to I. This is a condition that can be formulated entirely in terms of root system, so it's the same condition as in the group case. So you have these scattering operators, these are unitary and they're indirectly defined. Okay? They're indirectly defined in the sense that, a priori you don't write them in terms of standard intertwining operators. However, what I want to say today, well, one of the things I want to say, but I'm going very slowly, we'll see how much I will get to, is that these scattering operators involve L functions. So, fact, the scattering operators, fact and expectation, in some cases it is known, in some other cases the scattering operators involve not L functions but gamma factors. And here is one case that I know. So for a particular case is when you take I equals j equals the, my parametrization of the operators is not ideal, I'm realizing here. So when I equals j equals the empty set, like in the group case, you have to parameterize those by all Borels, all semi-standard Borels, all Borels that share the same levy. So, so in particular, the scattering operators are parameterized by the Weil group of X. And here is a theorem of mine, but I have to explain that this theorem, the way I will state it here, is not entirely written up anywhere. It is it's been written up for the unramified spectrum over periodic fields, and it's written up for rank 1 cases in general over arbitrary fields, but the combination of these arguments directly generalizes to prove the theorem in general. So here I'm going to take G to be a split group, and X is going to be a spherical G space. And I'm going to make a technical assumption. Let me make an aside here. What is this space X empty, the most degenerate one, the asymptotic cone X empty in general? So what is X empty in general? It is a horospherical case, a horospherical space, horospherical, which means that the stabilizers contain maximal unipotent subgroups. So stabilizers contain maximal unipotent subgroups, and more precisely, it looks like this. X empty is isomorphic to U minus L1 modulo G, where P, well, let me write U bar, P equals U bar L is a certain parabolic associated to X. For example, in the symmetric case, this is called a minimal split parabolic, theta split parabolic, and L 1 is some subgroup between the commutator, between the group of L and L itself. In particular, on this space you have a right G action and you have a left G action, a left action of L mod L1, which is an abelian group. Okay, I'll call this group AX, it is a torus. And the technical assumption that I want to make, just because otherwise the formulas get much more complicated, is that assume that L1 is torsion free. Okay? So now, of course, before I formulate the theorem, in order to formulate it, let me observe that this boundary cone can be written as the induction of this torus AX from this parabolic to G, and therefore L2 of this is L2 of AX induced from this parabolic to G. The letters are small. No. Sorry? This is L mod L1. L mod L1 is this torus, AX.
The assumption is that AX?
No, L1 is torsion free. L mod L1 is always torsion free, it's a torus. Well, it's not torsion free, it's a L mod L1 is, sorry, not torsion free but connected. Sorry. Yeah, connected, connected. Connected algebraic group, yeah, so. This is a technical assumption. This observation doesn't depend on that, but the theorem depends on that. And then the theorem says that then there is an explicit collection of pairs lambda comma S lambda, where lambda is a co-character of AX and S lambda is a half integer. Such that the scattering operator, let me only present the formula for the longest Weil group element. It doesn't, so this will be the longest Weil group element. Chi takes the place of sigma. Chi is a character of the torus, right? So chi is a character of this torus AX. And this is going to be gamma of S lambda product over lambda, gamma of S lambda chi lambda psi, either plus or minus 1, I don't want to get into these details here, times the standard intertwiners. Again, this is an explicit collection and it can be computed based on the geometry of your space. And let me give just some examples. I don't have time to explain how it's computed. So let me give some examples. example 1. The example 1 will not be exactly a space, it will be the Whittaker model. So I'm going to write it like this, and by this I mean whenever I write L2 of x, I will mean the induction from the maximal unipotent subgroup to G of some, well, this is, let's write this as uppercase psi, of some non-degenerate character. So in that case, the asymptotic cone, and sorry, just to fix conventions also, I think I want to put an n bar here. Think of it as a, whenever, anyway, let me not explain why I put n bar. So just, the asymptotic cone is the same space but without the character. So this is, so that means that L2 of the asymptotic cone is just the induction from the Borel, from the opposite Borel to G of L2 of the torus. So this is the torus. And in that case, the scattering operator decomposes the scattering operator. What will be the scattering operator here? The scattering operator will go from induction from B opposite to G of chi W to induction from B to G of chi, sorry, chi W inverse. And it's going to be given by the Radon transform times gamma 0 and check bar chi C. That means that the collection of weights here, lambda, are the weights of the dual torus on the dual nilpotent radical. So this is a product of abelian gamma factors. This is what the operator is given by. And another example is, so let me write this in the group case. In the group case, let's just write down the case of, we already saw what it is in the group case, but let me, just to compare with this, so example 2, let's take X to be the group SL2 or PGL2. So we already saw what the asymptotic cone is, and we have the formula here which in this particular case translates to the following. So here I need to put the intertwining operators for the group H, of course. And I get the same factor together with its opposite. So I get gamma 0 n chi psi inverse, gamma 0 n bar chi psi. And okay, this n is the dual n. And then let me write a third example. X will be PGL2 modulo the torus, the multiplicative group. And in that case, SW chi is going to be the same thing here, the same basic factor. well, this is for G now. And then this will be multiplied by gamma. So, but let me also clarify what is n check here. So we're talking about the dual group. The dual group is just GL2 or PGL2 or SL2. So n check here is the same as the positive root. So I could have written alpha check. So the lambda is alpha check because I'm in rank 1. And this here is minus alpha check, okay? And then in this case I'm going to get again minus alpha check, and here I'm going to get gamma of alpha check, well, gamma 1/2 alpha check over 2 chi C absolute value square. So why should you care about these formulas? Can I take 5 more minutes to explain? So I'll take 5 more minutes to explain why you should care about these formulas and where this leads to. So this is a story about L2 that I have said up to now, but this is not the whole story. One could try to ask for a description, so question, give a spectral description for the Schwarz space of X, that is, let's say, CC infinity of X. Give a spectral description for CC infinity of X. This is the Paley-Wiener theorem. So in the case where, so here's a theorem due to Delorme, Haring, and myself, when F is a p-adic field and X satisfies some condition which we call strongly factorizable, e.g. symmetric, all symmetric spaces satisfy this condition, then the theorem gives a description of CC infinity of X. Let me just, sorry, I cannot write CC infinity all the time. S will be CC infinity, okay? So the theorem gives a description of CC infinity of X, but it doesn't look exactly the same as for the Harris-Chandler-Schwarz space. It looks almost the same. So let me be naive and say that S of X should be again the direct sum over all i's of S of Xi, and then invariant under the scattering maps. What I wrote here does not make sense, and the reason it doesn't make sense is that if you think about it, of course before we had discrete, so here we will have relatively cuspidal. So this doesn't make sense because relatively cuspidal just means that when you embed the representation, its image is compactly supported functions modulo the center. Okay, and center is this torus acting. So this doesn't make sense because if you think of the spectral decomposition of something that's compactly supported and smooth, the spectral decomposition on a torus, for example, the spectral decomposition has to be polynomial. It's polynomial on the spectrum, right? CC infinity of Z is polynomials on the dual torus, right? But these scattering operators here have poles. Okay? So what I need to do is I need to enlarge my space, and take the original Schwarz space plus the images of the scattering operators. I'm not going to write it down, but that's the definition, the precise definition of this S plus. So you take the original Schwarz space, but you take also the images of scattering operators from associate J's. And then the theorem is correct. Let me give you, let me explain in these examples what are the implications of that. I want to prove using this theorem. So why am I interested in this theorem? I'm interested in this theorem because in principle, if you know this space, you know everything about distinguished representations. You want to know what are the quotients of this space, right? So let's take the Whittaker case, for example, and I want to prove to you something that is completely clear, that the trivial representation is not a quotient of the Whittaker space, right? So think of the Schwarz space, compactly supported functions on G mod n. Okay, so compactly supported functions on G mod n on X empty is through Fourier transform, you know, it's we're inducing from some parabolic to G what? Basically you're taking polynomial functions on the spectrum of the torus. So let me write A hat. So the spectrum of the torus, the set of its characters, is naturally a torus, an algebraic torus. You can, or rather a union of algebraic tori. You can make sense of compactly supported of polynomial functions there. But here, what does the, so at most points here, the induced representation is irreducible. But there are some points where the induced representation looks like that. It has a quotient which is the trivial representation and a subquotient which is the Steinberg. Or it has a quotient which is the Steinberg and a sub which is the trivial. And between those two there will be an intertwining operator. Now the standard intertwiners are taking this. How does the standard intertwiner work? It takes this down to here, right? But because of the pole that you have here, what will happen is you actually need to use the inverse of the standard operator. So you have to, how does it work? So basically this space S plus, so this here is a spectral description of the space S. And the space S plus will have an extra Steinberg here. This is why the Steinberg does not appear as a quotient of the Whittaker model. On the other hand, and I'll finish with that, let's look at PGL2 mod GM. Okay, I have the same factor, but then the pole that I had here is cancelled by a double zero here. So the picture that I have in this case at the same representations is that I hope you understand what I mean here. C is a quotient, still is a sub. So the picture that I get here is the opposite. So this is the standard Schwarz space, and this is the extended Schwarz space. So the extended Schwarz space will have another C here, and the scattering operator will take me up here, which means now that the Steinberg is not a quotient of, in this case, the Steinberg is not the quotient of the continuous summand. Where does the Steinberg lie here? It is supercuspidal. It is relatively supercuspidal in this example. Okay? So I just wanted to give you this feeling. I don't have time to go. I planned too much. But I just wanted to tell you that, you know, L functions, there is some L function associated to each of these spaces which determines the precise answer to, which should determine, I don't know the general answer, but it should determine the precise answer to the distinction problem. Okay? Of course, eventually, one should go into the categorical local Langlands program that has started being developed, and actually make an even more sophisticated description of this space than you see here. You would like to say that this space is a certain sheaf on the space of Langlands parameters. And I thought that I could have the time to speculate a little bit, to talk about my work with Bensby and Venkatesh and speculate a little bit on what this sheaf should be, but I don't have time for that, and I'm already way over time. I'm sorry for being so late.
Most of your lectures had only gamma factor at 0, but this example 3 had gamma factor at half.
Thank you so much for your question. So, there is some L function hiding behind. So, I started with an X, and I claim that there is a space X check hiding behind. And all of these spaces have an action of GM. So there is a recipe to extract the L function from this space. I don't want to take more time and explain what this space is, but there is a GM action here that will determine the point of evaluation of this L function. Okay? And maybe another thing that I want to say is that there's not always a space X check. Sometimes the only thing that we can construct is what is morally the cotangent bundle of X check without having X check. And those are the cases where I expect that there will be some epsilon factor determining the distinction problem. This is exactly the case where there is no X check. I don't know what is this sense.
Like the X-ray transform integrate over geodesic. So we are looking over everything, looking at the action on smooth.
Yes, I don't know exactly if that will satisfy you, but what happens here is that this scattering operator, so you have, basically what you have is you have maybe, maybe since I don't understand the question, let me not try to answer it. Yeah, but the point here is that these are not, the Radon transform is always the same thing. It doesn't see which space you are working on.
Yeah, so I'm saying that nanogeometry just analogy with the classical T0K and the motorcycle transform, everything.
Okay, I'd be very interested to understand what you mean. Thank you.